Good morning. My name is Kathy Zyme. You are at the presentation for Heat. It's not just your grandparents' forced air with George Lafontes and Suraj Lobo. Okay, on behalf of the Northwest Eco Building Guild, we acknowledge that we are all on the traditional land of the first people of this region. We honor with gratitude the land itself and thank the tribal people who have been faithful stewards of the land, the water, and the ancient history of life. Peace, dignity, and equality on a healthy planet. This is from the United Nations. It's simply stated, but it deeply resonates with our committee as we think about you and the need in our communities at this moment. We believe that you are the group of people to set an example for how to support one another and move through this time together to arrive at a better place. Please thank us in joining our sponsors. Our sustaining sponsors are Dunn Lumber, King County Green Tools, and Farrow's Creative. Our supporting sponsors are too numerous to mention, but we couldn't do this without them. So please make sure to check out all of these great companies. And finally, please note our contributing sponsors. All of our sponsors help make this event possible, so please help us to thank them all for supporting us. Before we get started, we have just a few housekeeping notes for you. When we finish our presentation, you'll see a show floor like in this picture. And I think most of you are familiar with using Remo by now, but if not, you can ask people who are sitting with you at your table to help. If something really doesn't seem right, many problems are resolved by simply moving to another table or leaving the meeting and coming back in. If you have mic and camera issues, look at the upper left-hand corner, that purple circle. You click on those 3 bars and that has help topics for that. For help from one of your hosts, look for a yellow star like you see enlarged on the right. All right, now I am excited to introduce you to our speakers for this session. Our speakers are George Lafontes with Mighty Energy Solutions. He spent more than a dozen years overseeing energy efficiency research for the largest private commercial developer in Philadelphia. He also participated in design and development of highly efficient small wind turbines, fuel-efficient aerodynamics for long-haul trucking, and shaped airflow innovations to save energy in open-case refrigerated displays like in the supermarket. His move back to Seattle provided the opportunity to apply his love for science and functionality to residential heating with Mighty Energy, where he spends most of his days modeling and designing heating systems that often apply a variety of efficient hybrid solutions. Suraj Lobo entered the mechanical trades as an HVAC technician in 1994. His passion for energy efficiency inspired him to open Progressive Comfort Solutions in 2009 to be of service for anyone with greater efficiency and comfort through harnessing ductless heat pump technology. I'd like to invite George and Suraj to the stage.
Hello, everyone. So I'm going to share our presentation now. I'd like to thank everyone for having us here today to do this, share our knowledge with you. Also, I'd like to suggest that you click the 4 arrows at the top of the presentation if you want to follow along with our slides and still hear us rather than having to just look at us as well. But in any case, I guess we can get started. Yeah. With these are the AIA slides. We'll let them run. And we will, at the end, the learning objectives are also reiterated in case that this timing isn't quite enough to read them. All right. So we're going to talk about how the all-electric home can be heated efficiently and why the all-electric home is really the only way to go. Suraj will talk about ductless mini-split heat pumps, and I'm going to be talking about infrared radiant heating systems. And together we'll get to how the hybrids of those can be a total solution. There is no silver bullet, but between the two, we can heat your home comfortably, efficiently, and safely. So get started.
Okay, can you hear me okay? Can you hear me okay?
I can.
Yeah, okay, great.
I'm good.
All right, good morning, everybody. So we typically talk about heat, and in doing so, we often want to get right to the efficiency, but we can often forget about these other factors that are really important as well. So comfort and health. And as we get to health, we'll see included within that is safety and social justice and so forth. But to begin, we can look at efficiency. Joey, can you forward us along? Thank you. So when we look at efficiency, we need to look at it as a whole. So the first thing we need to look at from the point of view of conservation is losing less heat, right? So our weatherization and our building envelope and so forth, plus less energy wasted. So we're asking a heating system to do work, and that work we're measuring in terms of units of heat. Anything that's not actual heat is a loss. So we're trying to minimize that loss and maximize how much of that energy that was the source turns into actual heat used. So that gives us less energy used as a whole. And what that means to us is less cost, less operating cost, and finally less carbon emitted as well. So long-term cost. So we can't proceed without a nod to our conservation folks. Definitely the first way to begin the conversation of efficiency is looking at how much heat is lost in a space, right? So these are things like windows and doors, insulation, air sealing, lowest hanging fruit, the envelope, what we call the thermal envelope of a space. And definitely that is the beginning part of the conversation. We're not going to spend any time on that here because that's both an assumption that needs to happen, and that's not the purpose of our presentation. I was thinking this morning, that's a nice little Pacific Northwest slide here. I was thinking this morning about my dog, and any you also have dogs. In the fall, he wedges his paws under us when he sleeps, and that's him trying to conserve his energy, just like in this slide, right? I mean, he could have all kinds of heaters around him, but really the simplest thing to do is to insulate himself from the outside elements. We can advance. Great. So when we look at efficiency, we're looking at how much energy is converted into heat. So here's a slide of a heat pump that is, heat pumps are sort of interesting, and we can look at this. So there's two ways to convert energy into heat, right? One is transferring it from one state to another, which Gio will look at later. The other is transferring energy from one location to another, and that's how heat pumps work. It's sort of unique. We're actually capturing heat from the outside air. We're transferring that heat energy inside through the refrigerant and then rejecting that heat in the space. We're not transferring any air from inside to outside, just heat energy. And then we're able to reverse that and do air conditioning as well.
So I'd like to talk about our top of the line solution, which is the Dukatera heat panel. You can see it has 4 parts. It interacts with the outside air, not at all. It's inside your home. It has a steel back panel and an high-tech aerogel insulation between the element and the ceiling, goes on the ceiling, and a unibody constructed aluminum casing. So it's basically a box. You can see the woman's holding the largest panel. This goes up on your ceiling, and it's a light, but it shines in infrared, which is the part of far infrared, in fact, which is the invisible part of sunlight right below visibility that we feel as warmth. So instead of shining light for you to see, it shines warmth, and it turns electricity into infrared light. One thing I'd like to mention very quickly about sustainability is this is a design that has no moving parts, so it lasts for decades, but also at the time when it does need to be recycled, it comes apart in 4 pieces and is easily recycled. So that's another aspect of the overall goal of being green with this type of energy. So this is big in red, and people often have accused me of going back to the dinosaurs whenever I'm asked a question, you know, like, tell me about the history of a pencil, and I'll go back to cave paintings. But in this case, we really do go back to the dinosaurs. We've been digging up and cutting down things and burning it for heat and light and cooking, etc., forever. And we have to transport that stuff. That takes energy. We have to, we had to gather it in the first place. That takes energy. If this oil train here were to explode, then we've done all of that and lost all of that energy. And so, not to depress anybody, I'm going to move on, but we have to get away from fossil fuels. Fossil should mean it's history. That's my personal opinion. We need to go to the all-electric home, and that's what both the mini-split ductless heat pumps and the infrared radiant heat will do for us. Now, luckily in the Northwest, we already have non-combustion electricity for the most part, not entirely, but for the most part. It's still generated in a centralized way and transmitted out, so we do lose some of that energy through transmission losses. And but the good thing about the all-electric home is, even as we go past using things like hydro to more distributed and co-located generation like solar and wind closer to where we're using it, the electric home will respond immediately, and that's what that immediate transition is about. You've got all of these homes that need to be converted to electric, but the minute you start producing that electricity more effectively, more efficiently, etc., all of those electric homes automatically respond to that.
Thanks, Joe. So the title of this presentation is "It's Not Your Grandparents' Forced Air Anymore." And so really, the way we've been heating homes for the last 100 years or so is both centralized and ducted, right? So there's some central piece of equipment that's hidden in the basement or the attic that is generating the heat, right? And then there's a bunch of ducting that is designed to move that heat via air throughout the space. So that's really problematic, and never assists us in terms of efficiency, comfort, or health and safety, right? Ducting always wastes energy. And the Department of Energy, in their estimation, has shown in existing homes that ducting can lose up to 50% of the energy generated by the heating system, depending upon if that ducting is in the unconditioned space, if it's not sealed or insulated, which anecdotally, Gio, I mean, you go in homes as well, I can tell you most homes that I see have ducts that are not in conditioned space, not sealed, not insulated. In terms of new construction, and this is for the architects as well, we are now putting ducts inside the thermal envelope, but they're taking up so much space and the need for soffits and so forth that it's very difficult, I would say impossible, to perfectly design a heating ducting system. And even if you've done that, to actually install that ducting system. And so this image shows all kinds of leakage happening. Depending upon where the leaks are, If the leak is in the return and the air intake side of the heating system, we could see all kinds of contaminants such as odors and carbon monoxide and so forth with backdrafting. And if it's on the supply side or the discharge side of the heating system, we see loss.
Okay, I just wanted to throw in very quickly, if we're doing renovations as well and you're demoing a wall and suddenly you find the duct that's there, that's you're gonna make a more open concept. You're gonna, have to figure out how to reroute that if you're gonna continue with that type of heating. Sorry, just wanted to. No,
thank you. Actually, I've seen so many of the homes we go on, some duct has been extended and just virtually nothing. Air is actually quite difficult to move in a space. Of all the fluids we move through a space, air is actually the most difficult. And anybody who's lived in a home with forced air will tell you that's the case. So here we're getting into one possibility, one aspect of shifting from the centralized ducted system, which is to zonal. And Gio will speak more to this as well in terms of hyperzonal. But one virtue of the ductless heat pump technology. So heat pumps were invented in America in the 40s. And really the Japanese have helped to really shift this technology to the next level by doing three things: by getting rid of the ducting, by making the systems ductless and zonal. So now there's indoor equipment that lives in each space that we're trying to treat. And finally, our systems are fully variable speed as well, which assists in terms of efficiency and sound volumes, et cetera. So here we can kind of see that this little diagram of a house, we have 4 indoor zones there. The idea is each zone can be controlled independently, turned on or off, up or down as needed. In most homes, the bedroom spaces are 10 to 20% of the entire cubic footage of the home. And when we're sleeping, we typically like that a little bit lower anyway. And so why do we have centralized systems where we're forced to choose either to heat the entire home at 100% of the speed of the system or none? When in fact, very often, we want somewhere in between. And so this system that's designed in this image is showing you that actually we get to do that. We get to turn each unit up or down, on or off as needed.
So you'll notice that my temperatures are slightly lower. That's because infrared works directly. It works in 3 different ways. It heats you directly with the infrared radiance, warming the floors and the furniture and the people and the pets and the walls. And then that, now you've got warm floors for your bare feet when you wake up in the morning to put down onto the floor, to go into the bathroom, which maybe has a tiled floor, and a programmable thermostat can come on before you do your morning routine in one of the most important rooms in the house that you use the least amount of time, and then it can go off. The bathroom can be on when you're likely to be using it, and off when you're not. And then the heat is shed into the air as well. It brings up the ambient air temperature. But what we have noticed is that people do in the rooms with the infrared heat tend to have their thermostats a little lower, because the more standard idea of having the warm air, which actually ends up heating the unused volume above you as it rises, can be in the direct radiance when they're using that space, and in that way not have to necessarily bring the temperature up to what you'd normally think of as a different kind of psychology. Also, you have a guest bedroom. Why should you be heating that unless you have guests? Maybe a laundry room that you might want to be warm when you're using it, but not when you're not. And then the hybrid part of it is that the large open concept spaces are very much more efficiently heated by mini split ductless heat pumps. We like to have our high ceilings and our big rooms, but sometimes you get cold spots throughout the house because it's not reaching into the back bedrooms or whatever. And so you can do a nice combination of infrared and mini split ductless heat pumps as a hybrid to be comfortable wherever you are in the house. Now, this is an interesting slide because there's a lot of ways to aggregate how these things are efficient. So you can see that we have the infrared at the top here, but this has to do with the cost of the overall cost of ownership. Mini split ductless heat pumps are more efficient than anything except for geothermal. If you're willing to spend the money to dig at a geothermal well, good for you, and that's great. Most people won't be able to do that, even if they could afford it, depending on the real estate situation. But that being said, because the infrared panels last for decades, the cost is amortized over a longer period of time. You'll also notice that the cadet wall heaters and baseboards, which are super inefficient, are higher up, but that's because they're basically big lighters. They last like 10 years and you got to toss them out. They are not that efficient. And then we get into things that are not electric, or they're centralized. So we go through all the things that Suraj said about the problems with ducting, etc. Basically, you end up with infrared and mini split ductless heat pumps being the best, most efficient in all the metrics that you could use. So now we get to comfort, because normally, you used to think, oh, I'm going to do something more efficient, more green, and I'm going to lose the what I really want, which is to be warm and comfortable, and just like a Tesla will beat a Bugatti in a sprint, you don't have to sacrifice comfort for efficiency. So basically what we're talking about is when you're going green, you're going better. So this is Suraj.
Thanks, Jim. So speaking under the heading of comfort here, we're looking back at this idea of being in the space that we're treating, right? So whenever you have ducting, you have delays and you have the inability to predict what that space needs, right? So when we get zonal, both of our systems do this, they're responding to the needs of that space, both in terms of the inhabitants, how many people are there, but also in real time, what's happening to the thermal needs of that space, right? Is the sun shining in? Has it gone dark? Is there wind? Is there less heat outside in the outside air? Is it raining? This interrogate in this image is able to respond real time and vary the amount of heat that's being delivered or air conditioning, and vary the amount of airflow as well. Yeah.
So if I'm reading a book, I turn a light on where I am. And like I said, infrared is light. And so I need to be a little warmer, and I don't necessarily want to get up and get that throw. My dad used to always joke, whatever happened to put on a sweater? Well, I don't have to now. I can turn on the infrared, and they will work with smart systems. So you could even ask Alexa to be warm where you are without having to affect the rest of the space. I'm pretty sure this probably will stop some arguments in families too, over control of the thermostat. All right.
So one challenge we have, and certainly architects face this as well, and builders, is actually designing the entire system to fit the needs of the space. And as you can see in this image here, right, we see a lot more vertical construction now as we shift towards urban density, certainly here in Seattle. And when you start to get more vertical with interior stairwells, you see lots of beams and so forth. And trying to get around a beam to move a duct is it's very challenging. Sometimes you can lose half the airflow of a single run just to get over one beam. So another value of ductless systems is we can route our refrigerant lines around virtually anything, including beams, and mount our systems in a space that's very discrete, that's really able to treat that space without sacrificing in terms of soffits and just construction elements that really impede on that space.
So one of the things that both of our of these systems challenges both of these systems kind of overcome that you find with a lot of green things is that we have track record. These systems, the technology has been around a long time. So you can say, oh, this is going to last with something brand new, some new innovation. But in our case, we can say it because it's been out there in the world. Now, with the heating panels we have, because you have to have insulation between the element and the ceiling, they used to be very thick. They were used for drop ceilings, Armstrong drop ceilings, that kind of thing. But nobody wants to hook a pizza box up to their ceiling. By using the Aerogel insulation, which is super thin, this high-tech insulation, you can see from this picture, it's about a ½ inch thick, goes up on the ceiling. It, because of the surface, the wattage that's going through a somewhat larger surface area, they don't get too hot to paint. So you can blend them right in with the ceiling. You can even flush mount them with the sheetrock in the ceiling. And so they're very unobtrusive. Designers tend to really love this because basically they're not there. They don't even have to consider really, except for the lighting plan, the electric plan in the ceiling. And so this makes it, it's not a big deal. It's not a space heater you're going to trip over or anything like that. So also we talk about health, and normally when we talk about health, we talk about cleaner indoor air, but health is also safety. People not being injured, the environment not being damaged, and the water, the outdoor air not being damaged, etc. And also efficiency means it's more economical. And all of those things actually speak to social justice as well. If something is cheaper, even if you don't raise the minimum wage, people are paying less for their utility bill. That's more just. If people are getting clean water, that's everyone. It's more just. And of course, if you have cleaner indoor air and you don't have good health care and your kid has asthma, that's more just. So this speaks to all of these things. We all want to be healthy. We all want to escape injury and toxicity, and we all want to spend less money. But but efficiency in this case is more fair for everyone, no matter what part of the economic spectrum they're on. So here you can see a panel. It's been painted to blend into the ceiling. And although this is a still image, I included this one because it has those little butterflies. And if this were a video, you still wouldn't be able to tell if this was on or off. Those butterflies would not be fluttering around. You wouldn't be able to hear it. It's just silent infrared light. It's not stirring up any particulates, and all it's doing is warming you up. It's not doing anything else to contribute to the noise pollution or the indoor air pollution.
Thanks, Joe. So another virtue of both of our systems is shifting from fossil fuels and shifting away from localized combustion, right? So whenever we combust a fossil fuel, we have byproducts. It's impossible not to. We'll never achieve 100% combustion. And so our goal with the heating, with a gas combusting appliance or an oil combusting appliance is to duct and remove those byproducts of combustion to the outdoor space, effectively kicking a can down the road, letting someone else breathe that air. But anecdotally, I'll tell you again, in the 25 years I've been in this trade, in so many cases we see instances of some particulate remaining in the space. It's invariable, right? And it's not typically to the point where it leads to death, but definitely chronic health conditions, headaches, and so forth, asthma. Combustion never helps. The body does not want to breathe the byproducts of combustion. So the very virtue of shifting away from combustion sort of really frees us from a lot of those things. And I can tell you anecdotally, in the retrofits we've done, we've seen asthma improve and headaches and so forth, just really chronic conditions that people face by virtue of breathing in those the byproducts of combustion, just relieved. In this instance, we're also seeing some added filtration as well. And so there are all sorts of accessories that can assist with filtration in terms of odors, in terms of allergens, mold, mildew, and even some case studies around viruses and bacteria, even COVID. We're seeing some cases come out with respect to that as well.
Yeah, and I just wanted to throw in that, you know, indoor air quality is generally not as good as outdoor air quality, but, you know, with the recent wildfires, et cetera, it's nice to have a filter, whether it's your heat recovery ventilation or your mini split ductless heat pump to filter that outside air, so you're not having to put a filter on your box fan to try to breathe inside your house.
Right, thank you, Gio. It's said that the indoor air quality is typically 5 times more polluted than the outside air. Again, all things being relative, right? If you're in Los Angeles, that might not be quite the case, but generally speaking, the indoor environment has much poorer air quality in terms of off-gassing and so forth.
Okay. So I'm bringing up another red flag here to talk about fossil fuels once more and hammer home about the all-electric home, because this is about natural gas. This is fracking. And where it starts is, you know, I worked in Philadelphia for over a dozen years. So I was in Pennsylvania, where fracking is a big thing in the middle part of the state. Whole economies exist around this, and it's destroying communities because they're making that choice. They're getting money from it, but now their tap water is in flames. You know, they're taking fresh water and polluting it in order to do this. And even if the parents are making this decision, the children who are going to be suffering most from the climate change it helps to exacerbate, they don't have a choice in this either. So they're having an immediate effect. This is having an immediate effect on people. So even if natural gas is in and of itself considered, somewhat efficient for heating or cooking or anything else, having those pipes come up into your house means that you're getting that fuel from this truly tragic, catastrophic approach. And we have to go to electric. And also, when we stop using gas, now you're going to have to convert anyway.
Thanks, Gio. So safer equals healthier, right? So to the degree we can get away from combustion, we achieve health. So here's an image of solar panels. Electricity, as Gio likes to say, is agnostic, right? It doesn't really care how it's generated, and the cleaner you generate that electricity, immediately the cleaner that energy source becomes. And so, we can even harness electricity localized right in our home, and eventually even store it as well, and be finally fully off grid. We have that ability now in terms of technology, and our systems are able to use electricity to convert it into heat and air conditioning in the most efficient way possible.
Yeah, I just want to throw in very quickly that this is hyperlocal generation, distributed and co-located generation, which would be optimal. I showed that hydro dam earlier. It was mismanagement exacerbated by climate change that allowed high tension wires to cause the campfire. So electricity in and of itself is still problematic. The dams are problematic. They affect our fisheries, et cetera. And out here, that's the entire ecosystem being affected. So the more we go towards solar, big nod towards people doing that, and generating our power closer to our homes, the better. But again, if your house is set up for electric, it doesn't care. The minute you make it better, it gets better. All right, Suraj.
Thank you. So here we have a home that was recently designed in South Seattle. It was a net zero house and using a lot of existing materials and so forth. And so, this technology, it's here. It's definitely scalable. We've come a long way already. I would say we've already arrived, right? So many of these technologies we're looking far into the future. But in terms, whether we're looking at LEDs or, as Gio was saying, with driving the electric car and heating as well, we can see the electricity is actually our ability to convert electricity into energy and heat and conserve it in a space. We've already arrived.
So I'm going to bring up, I guess this is a little bit of a case study to talk about scalability, but also talk about social justice. There's an organization, a great organization called Facing Homelessness, that in partnership with a wonderful architecture firm called Block Architects, started building these tiny homes for the homeless, working in a community with a specific homeowner to place them in their yard, but working with the entire neighborhood, which to build these tiny homes, which not only gives a homeless person a home, but gives them a community of people with homes in a neighborhood. And as it turns out, for the past 3 years, Dukatera, the manufacturer of the panels, and Mighty Energy have been able to contribute to this by donating the panel that heats this home. It's a small footprint. Now we're going to go to smaller and smaller footprints, and sometimes any other form of electric heat just wouldn't be, it'll take up space. It'll work in this smaller footprint approach, this higher density, smaller footprint approach. More and more people will be living in smaller spaces that just don't need the equipment to handle large square footages. So this is a unique opportunity for this solution. I really don't know if you could find a better one than to have this infrared panel in your small space. So these are our learning objectives. They were on the front slide. You didn't have a chance to read, but we hope that you now have an understanding of how what infrared radiant heat is, how it works, and how it offers a unique energy efficient solution to a lot of different heating challenges. And again, how heat pumps work, the energy efficiency there, also the opportunity to cool your space, and that it works great in larger open concept spaces. Finally, how the two together can basically cover almost any heating challenge you available using nothing but electricity. And then it's also important to note that there is a lot of inventory out there that uses inefficient heating systems, and we need to upgrade that. Not just build new stuff, that's great, but we need to be able to go and retrofit things. And again, these solutions are readily available for retrofit. You're not going to have to throw in a bunch of new ducting or pull gas lines up or anything like that. You simply put the units into the home and you're good to go. So I guess that concludes our little talk, and we'll take questions. Hang on 1 minute.
Thank you, guys. So far, we have one question, but sometimes it takes a while for questions to filter in. So our first question is from James Burke. When can we expect to have refrigerants with less carbon warming potential than ones like the R410A?
Well, we're getting into some policy things here. I can tell you in Japan, they've already started shifting into using carbon dioxide as a refrigerant. And in so doing, I mean, there's some downsides, much higher pressures, but there's case studies of 100,000 systems without any leakage or explosions. Their operating pressure. So, R22, the old refrigerants would operate around 125 PSI. We're operating now with the R410A at like 550 PSI. And so these CO2 systems can run at around 1800 PSI. There's some issues with building codes and UL listing that might prevent that from happening. But the point is that the technology is there. There are some sort of policy challenges that are above my sort of pay grade to really influence in terms of that getting here. Quickly going back to what Gio was saying earlier in terms of geothermal, with heat pumps, we use a certain terminology we call COP, or coefficient of performance. So we're putting 1 unit of energy in, 1 kilowatt in. Typically electric heat, we get 1 unit out. We get 3,412 BTUs out. For American heat pumps, we might get 2 units of heat out, so about 7,000 BTUs per kilowatt. With ductless, we get about 12,000 to 14,000. In Japan, as they've shifted to using CO2 as a refrigerant, they're getting about 5 units of heat out, which is what we get with geothermal at a fraction of the cost and using outside air, which is readily available. So I would say the technology's there, just not in America yet.
Great, thank you. Our next question is from Rob Valente. Regarding radiant panels, please discuss the variety of sizes of panels, sizes of rooms that can be heated, and the cost, and how localized is the sensation of warmth?
So the panels, the thin Dukatera panels are all just under two feet wide, and they range from 2x2, 2x3, 2x4, and 2x6, and each of those has a different flavor of wattage. So the way we figured out is we look at the performance of the home, the insulation, the windows, how well it's sealed up, and then the ceiling heights can matter because it is a light. The radiance shines down at a 45-degree angle. Luckily, that takes all the trigonometry out of it. If it's an 8-foot ceiling, then the radiance is going to hit 8 feet away from the edge of the panel. And so we look at all these factors and figure out how many watts per square foot should go into that space. Typical bathroom, might be a 250 watt 2x2 panel. Sometimes a larger bathroom, you might have to do a 3-foot panel at 375 watts. There are lots of factors involved. Is it primary or secondary heat? Are you combining it with the mini splits or some other heat source that you have in your home? But yes, you're going to feel the warmth within minutes of the panel coming on. It's not quite like flicking on a light switch, but it's very close. And that you will feel that right away, regardless of the ambient air temperature in that given moment. If you're standing in the sun outside as opposed to the shade, everyone will notice the difference in their comfort, even though the air temperature hasn't changed. And then, of course, because it's inside of an insulated envelope, the heat shed into the air does bring the ambient air temperature up and give you that kind of comfort. The cost for the panels themselves, the smaller panels are right now a little over $1 a watt, and then it drops below that. So probably about $1.25 a watt down to about 65 cents a watt. So a 6-foot panel, 1,000-watt panel would be about $600. The most expensive would be about $625 right now at retail. The contractors can get them for less, of course. So, but I'm not sure I fully answered the question there, but I don't want to ramble on, which is my tendency.
No, I think you got it. You hit all the points: the size of panels, rooms heated, and the cost, and how the warmth feels. So the next question is about mini splits. It's from James Burke. What is the life expectancy of mini split heat pumps, and how are the components recycled?
Oh, your mic.
Right. I want to mute myself for Geo. It's a great question, and anecdotally, I don't know. And the reason is I touched my first ductless heat pump about 12 years ago. We really started to see it double year over year in terms of number of units installed in America in the last 10 years or so. In Japan, they started designing these systems about 30 years ago, and we still see some of them out there. In fact, one of the first installations in Seattle, I found out, was in the Ford dealership in Northeast Seattle, where we got our vans, and that thing's still running. So it's been about 12 years there, and so we really haven't come up on the end of the lifespan of these systems. Largely, and maybe there's a little bit of a difference between our systems from Geo, which is, I mean, as you say, Geo, there's no moving parts. It's very few things to fail. It's actually hard to install incorrectly as well. Probably also hard to design incorrectly. I would say with our systems, one challenge is it's definitely easy to design poorly and certainly easy to install poorly. In the hundreds, if not thousands of systems that we put in, we have 0 failure rate. So we haven't seen any need to decommission a system yet. I don't know.
Question following up on that, and that is, so I'm an architect designer. How do I help my clients get a system that's designed correctly? Like, do you just have to go by the reputation of the heating company?
Is that for both of us?
Yeah.
Gio, you want to go first?
Sure. Well, the factory in Bellingham that makes the ceiling panels, we do sell other products as well, but the factory in Bellingham that builds the ceiling panels, Dukatera, they have the intellectual property on this. So and they have a lifetime warranty on the product. So if you get them from us, I mean, I don't know what you could do better than that. Obviously, you know, any company could go out of business, but again, no moving parts, etc. It's you could buy them from us. There are other people who can sell them to you. Installing them is no harder to install than a can light. You have to cut a hole for the handy box on the back of it, which would be like the recessed lighting hole, only you don't have to be as accurate. There's every 2 feet, so depending on the size of it, there's a sheetrock anchor. They're light enough, they don't even have to go into studs. If they can, that's great. So it's really pretty straightforward to install them, pretty hard to install them incorrectly. You do have to think, you know, in advance about getting the right ones, and so, you know, I would suggest coming to us, but they're pretty straightforward kind of formulas for how to get the right answer.
Yeah, when I've used the infrared heat panels on a project, we got them through Mighty Energy, and you guys were able to provide good consultation for what size panels we needed for which rooms. But is the same with mini splits?
Yeah, I mean, I would say it really just depends on who you talk to, for sure. We do free consultations as well, so we're happy we help architects. Probably a few people on now. We also give a lifetime warranty in terms of our work. Mitsubishi gives the longest warranty in terms of their equipment, which is 12 years on all parts, which is pretty substantial. As I say, I don't think currently, since that warranty's been out, nothing's exceeded that warranty yet. In terms of design, so I'm sitting in a showroom here in Seattle where we have all the equipment on display. When we look at designing a ductless system, we're really looking at 3 variables I call the 3 C's of ductless design. So cost, comfort, and cosmetics. Cost versus comfort is quantitative. It's how many pieces of equipment. Cost versus cosmetics, as we were seeing in those slides, is qualitative. It's, you know, what are the styles of equipment? And the further we get away from the standard wall units, the more the cost. And so really it's sort of playing with these variables to find the the most ideal solution. And what's most ideal, it depends on who you ask. The challenging thing with new construction is, a bunch of people are being asked to design a system for an end user who we don't even know who that is yet, right? And so, I think, but playing with those three variables, we can always find a system that can meet most of the needs, especially as a hybrid solution.
We have another question for Rob Valente regarding the mini splits. Please discuss strategies for handling the draining of condensate when they are in their cooling cycle.
So this is actually a really simple one. There's some, I would call it odd tendency. This technology has come from Japan, and whenever we see that happen, right, probably even to some degree with like electric cars and so forth, there's a little bit of an uptick in terms of knowledge of the people working on these systems. So with the drainage, there's this tendency to use this corrugated flexible tubing, and whenever I've seen it, I've seen nothing but problems. We never use that. We use rigid PVC piping, and we have very, very few to no condensate issues. And so it's easy to be done right if you use standard building techniques. It's when people are trying to use something that's off the shelf at Home Depot, or what their vendor says, hey, this is what the Japanese do, which is the case, that we start to see those problems. You're welcome to send me a direct link if you have any specific questions, but in terms of new construction, we run PVC drain in the walls every day, all day. Our crews are doing it today. We have absolutely no issue.
So I don't see any more questions. Is there anything else you guys want to say to wrap this up?
Just thank you for having us. It's been a pleasure and a privilege.
Thank you as well. And actually, I want to just thank Gio, because Gio has actually done all of the heavy lifting in terms of creating this presentation. So thank you, Gio. It's fantastic.
No problem.
Great. Thank you guys for sharing your knowledge, and goodbye, everyone.
All right.
Bye.